This is the New England Journal of Medicine COVID-19 update for December 21st, 2022. I'm Stephen Morrissey, managing editor of the journal, and I'm talking with Eric Rubin, editor-in-chief, and Lindsey Baden, deputy editor. Eric and Lindsey, I'd like to start with an announcement. In the midst of the holiday season, we'll be taking next week off. And given that, I thought that we should get an idea of where we stand at the end of the year, particularly when it comes to vaccines. Several countries, including the United States, have moved to using bivalent vaccines. So what are these vaccines and how do they differ from the earlier versions?
Steve, all of the widely used bivalent vaccines are similar in many respects. All of them are mRNA-based, and all include the original viral sequence that was derived from the spike protein of a viral isolate from the beginning of the outbreak in Wuhan. However, in addition, the vaccines contain a second sequence derived from Omicron variants. There are two different flavors: a bivalent vaccine containing sequences derived from a BA1 isolate and another based on a BA4, BA5 isolate. In the US, we're only using the latter, while both types are available in much of Europe. Thus far, and to my knowledge, there are no approved bivalent vaccines using other delivery platforms, though there has been some testing of protein-based vaccines. Given the long timelines for protein vaccines we've seen thus far, however, it might be a while before these become available.
So, Eric, you highlight a couple of important points. One is how the vaccine or the immunogen is delivered, which is the vaccine platform, and the speed of development, manufacturing, scale up of protein and viral vector delivered immunogens are just different than what we see with mRNA technology. That's an important consideration as we move forward and think about which types of vaccines or immunogens can be scaled up rapidly in response to a rapidly changing environment, as we've seen with the emergence of Omicron a year ago. In addition, you point out the insert, or what is the immunogen, and how do we manipulate that insert or immunogen to bring out immunity against the target of interest. In this case, it's the emergence of Omicron, whether it's BA1 or BA4-5, and how can we leverage these technological platforms to be responsive in a kinetically appropriate fashion for how the virus is evolving. I do want to point out that there have been multiple types of bivalent vaccines that have been designed, manufactured, and even studied, such as for the Beta variant, the Delta variant, as well as BA1, BA4-5. And how these different types of immunogens have behaved individually and together has allowed us a better understanding of their safety, their manufacturability, as well as the immunogenicity or the immune responses they can elicit. And as someone who's been involved in some of these studies, it's been remarkable the speed with which these types of immunogens can be designed based upon circulating sequences and vaccines potentially delivered to the clinic. Overall, the implications of these concepts, as you have alluded to, speak to how do we have technologies that we can use to be responsive to changes in the pathogens that we are trying to respond to. In this case, the emergence of the Omicron variants a year ago, and having vaccines that are deliverable to the community that are likely to elicit more favorable immune responses.
I think it's important to point out that the idea of multivalency or combinatorial vaccines is not a new one. And in fact, many of the vaccines we use routinely have combinations of antigens. The annual influenza vaccine contains either 3 or 4 antigens, each one derived from a different viral variant. The pneumococcal vaccine, which is directed against a bacterial pathogen, Streptococcus pneumoniae, contains as many as 23 different antigens from different strains. On top of that, we have vaccines that combine antigens from completely different viruses like MMR. So we know that the concept of delivering multiple antigens at once works. This isn't new. So there's every reason to think that this should be an effective way of protecting against disease.
And the COVID vaccines we're using now, these bivalent vaccines, how well do they work?
I think that before we give a score to these, we need to think about what the important goals are for these vaccines. When the mRNA vaccines were first introduced, They were incredibly effective at preventing infection and probably at limiting transmission. However, as COVID-19 has gone on, with the appearance of new variants, the vaccines have become progressively less able to prevent infection and mild to moderate disease. They do seem to have retained the ability to protect against hospitalization and death, though. So our goalposts have moved, and I think that it would be great if the newer vaccines produced at least some short-term protection against infection. So the goalposts have moved, and while I think it would be great if the newer vaccines produced at least some short-term protection against infection, at this point, the priority is to stop people from dying and to free up hospital beds. This means that it takes a while to assess vaccines because it takes a while for those endpoints to be measurable. Our initial yardstick for the performance of a new COVID vaccine is its ability to induce protective antibodies. By that criterion, the bivalent vaccines have had some success. They certainly are able to induce better neutralizing antibody titers against a variety of strains. However, this success is being challenged as new, more divergent strains started to appear. For example, today we published a small study of the ability of serum derived from individuals who'd received either 1 or 2 monovalent boosters or 1 bivalent booster. To summarize the results, the bivalent booster resulted in better neutralization against BA1 and BA5, even than 2 monovalent boosters. But it's important to remember that BA1 has disappeared and BA4, BA5 are almost gone. These have been replaced by more divergent viruses. In this studies, while titers were fairly high against the 2 viruses I just mentioned, they did decline a fair amount against strains like BQ11 and XBB, which are now circulating. So what does this mean clinically? It's still fairly early to measure the effectiveness of these vaccines in preventing infection. And when we get those numbers, they will be a little bit difficult to interpret because the population that's being vaccinated is very heterogeneous in terms of their prior vaccination history, the timing of those vaccines, and the incidence of infection in those individuals. And fortunately, hospitalization and death rates have fallen. So it will take longer until we have a good sense of whether or not these vaccines prevent the worst outcomes. It's likely that when we do get those numbers, unfortunately, they'll be useful only for strains that have already been replaced by new strains. So we're constantly going to be playing catch up as long as we have a similar vaccination strategy.
Eric, I think you raised an important point about moving goalposts and yardsticks that we use to measure success or failure. As we think about what success looks like for vaccination and our prevention strategies, we have to carefully reflect on goals that we had 2.5 years ago when we had initial efforts to control the spread of SARS-CoV-2. There, our initial assessments were in part related to what technologies we had available and our understanding of viral infection. And preventing mild to moderate infection was an important goal, and ultimately preventing hospitalization. 2.5 years later, where we are now, infection is rampant in our communities, but hospitalizations remain low in comparison, although they are increasing this winter, in part related to more vulnerable individuals getting infected, in part related to other viruses that are circulating. But what we are seeing in our hospitals, and this will be a challenge as we measure efficacy and success, is in patients who are admitted to the hospital and have COVID. Are they admitted due to COVID and COVID-associated illness, or are they admitted for another medical condition and happen to have COVID? And we are seeing both scenarios play out. That will be a challenge as we try to understand the benefits of vaccination and prevention strategies, as well as the burden of illness. And the burden of illness will be difficult to assess, as you know, as our testing approaches change, particularly with the increase in home testing, which is terrific, but the inability to easily track individuals diagnosed that way. Another goalpost that we are reflecting on, or yardstick, and I think is important for us to think carefully about, is how do we measure protection in the lab, in vitro? Antibody titers, neutralizing antibody, as you point out, when we look at sero studies after vaccination or from individuals previously infected, and we look at how it neutralizes BA1, BA45, BQ1, XBB, we are inferring that neutralization is the signature of protection. It may well be a marker of protection. It may well be important to protection, but there likely are many other aspects of the immune response that afford protection and ameliorate illness and severe illness. And I think in the US currently, hybrid immunity, either vaccine-induced or infection-induced, is widespread and likely to diminish severity of illness in the future. This is in contrast to what many of us are worried about may be going on in China, where change in their approach to stopping infection and infection spreading more widely may lead to more severe illness in the short term. And this is the nature of what we have to deal with as infectious diseases spread into different communities. So I think, Eric and Steve, it's very important that we think carefully about the goalposts and yardsticks we use to determine what is beneficial and how much illness we are seeing, because circumstances have changed and may be different between different very important communities.
Eric, you said that we're constantly playing catch up. Are there vaccine strategies that might allow us to get ahead of the game?
I think the answer is we don't know, but there are some things to consider. For example, we're looking at using antigens that are relatively close to one another right now. But it might be that more divergent antigens from more distantly related viruses can induce broader immunity than these rather closely related sequences that are being used right now. And there is some evidence for that in small studies. Also, it could be that different routes of administration can induce different types of immunity that give something that gives better protection or perhaps even broader protection. We've talked a lot in the past about using mucosal vaccines, but different methods of delivering those vaccines might also make a difference, not only the route of administration, but the method of delivering those. That's pretty speculative. We don't really have any evidence for that right now. But I think that Lindsey just made a very important point, which is thinking about the population that is receiving these vaccines. In China, there's a relatively low rate of prior infection, in fact, an extremely low rate nationwide. And that means everyone there is naive to infection, and vaccines have to do a very different job than they do in most of the rest of the world, where the rates of prior infection and what Lindsey referred to as hybrid immunity are going to be very, very high. So we really should be thinking about vaccines for most of the world that work well on the background of prior infection, as opposed to what we were looking at before, which is still the situation in China, looking at infection-naive individuals.
So, Eric, you raised the point about different types of vaccine strategies that may improve the immune responses elicited. And delving into this a little deeper, as we think about the antigens, as we've been talking about, there are different strategies to develop antigens that may elicit, Steve, as you ask us, broader immunity. One strategy, which are the approach to the bivalent or multivalent vaccines, are you take antigens or spike proteins that are as divergent as possible, and you use them to bring out broader immunity because the immunogens look very different. Another strategy is to look for conserved epitopes or regions of the viral coat that don't change across the species of influenza or SARS-CoV-2 and are exposed, thus vulnerable to attack. So there are different scientific strategies, and it's encouraging to see different strategies being pursued for the respiratory viruses of import, as they may enable us to develop vaccines that are broader and in the immunity they elicit to the circulating strains, and to potentially future strains if truly conserved epitopes can be identified. What also is important here, as Eric alluded to, is compartment. Does the mucosal compartment behave the same as the systemic compartment? Is one more important for severity of illness and the other for transmission? And do we need to understand the biology in the different compartments? And much science is going on in these arenas that can allow us to exploit the differences to enhance immunity where we need it, to have a salutary effect on illness, which I think we've achieved, and to improve the effect we can have on transmission, which needs much more work. And one last element that we all have been thinking about is the durability of the immune response. And that is something we've learned with the current vaccine strategies, particularly the mRNA strategies. The responses don't seem to be as durable as we would like. Whether it's due to the vaccine, the immunogen, the change in the virus, there are many questions here that have to be understood. But there may well be strategies where we look at different vaccine platforms to see if they can bring out immune responses that may be more durable or broader. Science needs to be done here for us to understand the potential, but we have many more tools now than we did a year ago or 2 years ago. And I'm certain we will see data emerging that will help inform these different approaches and combination of approaches.
To pick up on your last point, Lindsey, I think it's really important to think about the fact that we're using already very different tools than we did only a few years ago. We've learned a lot over the decades that we've been making vaccines. However, I'm not sure all the same rules will apply as we look at different vaccines and different ways of delivering them. So although I know that there is a feeling among some in the community that we're doing about as well as we can, I'm not sure that that's fair. I think that we might be able to do better, and we'll learn about that as we try these new approaches.
Nonetheless, from everything you say, it's clear that making vaccines that have lasting effects is going to be challenging. So is there any good news we can take into the new year?
I think there are several good stories. Remember that we're doing a lot better. Hospitalizations have fallen dramatically. Death rates have dropped dramatically. There are still populations that we need to reach in order to further improve, and there might be technologies that we can improve on that will also bring these numbers down. And I don't think that addressing the issue of infection is out of reach. It's something that I think is still on the radar. But clearly, we know a lot more about the pathogenesis of this disease, and we're learning more about what immunity means. Lindsey already alluded to the fact that there are lots of different kinds of immunity, and we've been measuring antibodies largely. We have measured other sorts of immunity, but we don't really understand what those numbers mean right now. And I think we're going to learn more about that. And as we do learn more, I think there will be dividends to come. And I keep in mind that while we're discussing vaccines, treatments have improved markedly. There are now good outpatient treatments. There are more on the way. And I think that we're going to continue to be able to decrease the morbidity of disease and the mortality induced by disease in the coming year.
Steve, I actually view this whole discussion as good news. I would look at it the other way around. In the 3 years since this virus emerged, and it was 3 years ago, it was December of 19 when it was first emerging, and January when the world really appreciated it. In this 3 years, we have been able to define the pathogen, define the pathogenesis of illness, understand immune dysregulation, understand viral parameters, and develop multiple countermeasures, vaccines, treatments like monoclonals, small molecules, as Eric mentioned. We've also been able to not only deploy these interventions to communities that need them, we've also been able to respond to viral evolution. It's not a static problem. And the ability to identify escape mutants and other aspects of viral pathogenesis that's emerging under selective pressure in real time, I think is terrific and allows us to then adapt our therapies to be appropriate to changes in the pathogen. I think it's remarkable that all this has occurred in the last 3 years, or 2 years in particular, in relation to treatments. However, it's still incredibly frustrating, the burden of infection that is going on globally as well as domestically, and that we have to continue to respond in a way that's proportionate and appropriate to the diseases that SARS-CoV is causing. But I actually am full of hope that scientific progress enables us to be responsive and to go to scale as quickly as we have done. It doesn't mean there aren't plenty of challenges, But as we go into the new year, I think we should be inspired with what science can do for us if we allow it.
Over the 3 years that the epidemic has been around, the world has changed. And mostly it hasn't changed for the better. Now we are much more restricted in the kinds of things we can do. We've had these large economic shocks to the world associated with lockdowns and the social costs and consequences of those lockdowns. But it's really important to reflect on how much better things are now. 2.5 years ago, everyone was staying home. Businesses were shut down. You had to walk around on the street with a mask on. Now, people are getting together for the holidays in ways that they hadn't been able to do for years. There are good tests available for those who are at particular risk that can make any gathering much safer. And when people get sick, there are better treatments for them. So I think the news is good. It could be better, but that's hopefully what the new year will bring us. Some improvement on what's already a much better situation.
Eric, if we're expressing our hopes, I would also hope that we can apply what we've learned and the technologies that have been developed to the other respiratory pathogens we're facing. I think flu, RSV, and others are pathogens we can have dramatic effect on. If we put our efforts in the right direction, we can tackle so many more pathogens that cause so much illness. So again, I am full of hope, but I think there are miles to go before we sleep, as I've said before. And there are many, many more medical problems we can solve with the kind of focus and energy that we have brought to responding to SARS-CoV-2.
Thank you, Lindsey. And thank you, Eric.